I now want to look at dimensionless numbers. I'll start with the Reynolds number, which is used to compare the effects of inertia, the effects of viscosity and fluid flow. And it's given by the density of the fluid times some sort of characteristic velocity. This might be an average velocity if you're talking about flow through a pipe, or it might be a far field velocity if you're talking about flow over a flat plate. Some sort of characteristic length, which for flow through a pipe would be the pipe diameter, for flow of a flat plate would be the length of the plate, divided by viscosity. And you'll notice here, actually, to show that that is dimensionless, I've broken down the viscosity unit, so I haven't expressed it as Pascal seconds, but rather in kilograms per meter per second, which is actually the same unit. And you can see from putting it like that that all the terms will cancel out. So we've got meters times meters to the minus 3 times meters, which should give us meters to the minus 1 over meters to the minus 1, so no meters. Seconds to the minus 1 over seconds to the minus 1 again cancels, and kilograms over kilograms also cancels. So this combination overall has no dimensions. It is a dimensionless number. Now, one of the things that the Reynolds number can be used to do is to tell us about where you will go from laminar flow to turbulent flow. So in laminar flow, the motion of individual fluid particles follows the streamlines. You've got a simple flow, whereas in turbulent flow, the motion of any individual particle is very complex and only follows the streamlines on average. And there are again some links there to YouTube videos which will enable you to see the difference between these two types of flow more clearly. Overall, from a heat transfer point of view, turbulent flow gives you greater mixing and therefore greater amounts of heat transfer. And also, laminar flow is technically reversible, and again there is a YouTube video there to link to have a look at to show that reversibility, although strictly some losses will usually occur, whereas turbulent flow is completely irreversible. So overall, turbulent flow, greater mixing, greater heat transfer, and is an irreversible process. I already said that the Reynolds number tells us about the transition from laminar to turbulent flow, and essentially there will be some critical value of the Reynolds number, and if the Reynolds number is less than that value, the flow will be laminar. If you're greater than that value, the flow will be turbulent. That critical value will depend on the geometry that you're dealing with. So for flow through a pipe, it's 2,300. For flow through over a flat plate, it's 5 times 10 to the 5. And I've just shown an image here, and you can see this is a region of laminar flow, and above here we've got turbulent flow. So once we're into this region, we'll be at higher values of the Reynolds number. When we're dealing with convective heat transfer, it turns out that most of the temperature and the velocity changes actually occur near the surface of a hot and cold surface, and that region of the fluid is known as the boundary layer. Unfortunately, there is actually both a thermal boundary layer and a velocity boundary layer that are not in general the same in terms of their thicknesses, but nonetheless, in both cases, the changes in velocity or the changes in temperature are limited to a region near the surface that we're dealing with. So I've shown a couple of cases here for what we call forced convection, which is where there is an external force providing the motion of the fluid, and in that case, if we had a heated wall, there would be a thermal boundary layer where the temperature would start at the wall temperature and it would drop down to the far field temperature, and at that wall the velocity would be 0 and it would rise to a far field velocity. What I've tried to show here is that the thickness of that thermal boundary layer and the thickness of the velocity boundary layer are not in general the same. With free convection, then we're under conditions of Prandtl number roughly equal to 1, and then the boundary layer thicknesses are roughly the same. So here, heated wall again, the temperature then drops down to the far field temperature. In this, with the velocity, it's 0 at the wall, rises to a maximum value because the flow is being generated by the fact that you've got a heated fluid and it's rising in a gravitational field, and then as you get a long way from the heated wall, the velocity drops back to 0. And I've just indicated that those boundary layer thicknesses can be compared via the Prandtl number. The Prandtl number is actually given by the specific heat capacity times the viscosity of the fluid divided by the thermal conductivity of the fluid, and is therefore a measure of viscous effects to thermal conduction effects. And again, if you work through the dimensions of the things that we're dealing with, you can show that this is actually a dimensionless number. Because the viscosity is involved, you get rather different Prandtl numbers for different types of fluids. So for liquid metals we tend to have very low Prandtl numbers. For gases we have Prandtl numbers of around 0.7 to 1. In fact, for many gases in many problems you can get if you don't know the Prandtl number, you can assume it's about 0.7. Although obviously if you do have enough information to calculate it, you should calculate it. Water, slightly higher values of Prandtl numbers. Light organic liquids higher still, and then when we get up to things like oils and glycerins, viscous fluids, then we get very high Prandtl numbers. And what this is basically saying is that except for liquid metals, the thermal boundary layer thickness is usually less than or possibly equal to the velocity boundary layer thickness. And if we're dealing with free convection, as I've already mentioned, the Prandtl number is typically the order of 1, hence the boundary layers are actually of similar thickness. Another dimensionless number, which is a measure of convection in fluid compared to conduction in fluid, is the Nusselt number, which is equal to HL over K. Now it is important to emphasize the fact that this thermal conductivity is the thermal conductivity of the fluid, because the bio number looks essentially identical. I originally introduced it as HV over Ka, but that can be equivalently written as HL over K. But in that case, the K value is the thermal conductivity of an adjacent solid. So the Nusselt number applies purely to a fluid. And again, just an indication of the dimensions to show that it is actually dimensionless. One other number that's relevant for free convection is what's called the Grashof number, which accounts for buoyancy effects and includes the volume coefficient of thermal expansion as well as the acceleration due to gravity. This essentially replaces the Reynolds number when we're dealing with free convection type problems, and again you'll see that the viscosity is involved, although in this case it is the square of the viscosity rather than just the viscosity. And to fully quantify convective heat transfer, it is necessary to undertake a full thermal velocity analysis of the boundary layers. Now this involves dealing with several quite tough equations. So we've got our generalized heat conduction equation, continuity equation, the Navier-Stokes equations for fluid flow, and fortunately it turns out you can actually make a two-dimensional approximation for dealing with boundary layer analysis. However, such an analysis is still mathematically very involved and is beyond the scope of the course. There are some details given in Holman, and you will find some additional notes outlining such an analysis on the MOL site, although you're not expected to be able to reproduce that analysis in any form. Really the significant thing that comes out of it is that for forced convection it turns out the Nusselt number will be some function of the Reynolds number, the Prandtl number and shape, and for free convection the Nusselt number is some function of the Grashof number, the Prandtl number and the shape. And in this course what we will therefore use are tables of these relationships for particular geometries, and essentially what we would do is from various properties of the fluid which would allow us to calculate the Reynolds number and the Prandtl number, we'll use an appropriate relationship, then calculate the Nusselt number, and from that you would be able to evaluate what H was for that fluid in that particular geometry. So as an example, for forced convection over a hot planar surface at a uniform temperature, then if you're in a laminar flow condition, then the local Nusselt number will be given by 0.332 times the Prandtl number to a third times the local Reynolds number, so this is Reynolds number at a particular distance along the plate, to a power of a half. or if you averaged over the entire plate, then the average Nusselt number will be given by 0.664 times the Prandtl number to a third times the Reynolds number for the entire plate to the power of a half. If you now move into a turbulent flow regime, then the Nusselt number is equal to 0.0296 times the local Reynolds number to the power of 0.8 times the Prandtl number to 1/3, and then I give an equation here for a laminar to turbulent case, giving an overall average Nusselt number related to the Prandtl number to a third, the Reynolds number again to power 0.8. So this will apply to an entire plate where you have a flow that changes from laminar to turbulent partway along the plate. And in this graph I show how that average Nusselt number varies with the Reynolds number as the plate gets longer, and I've also shown that for different values of the Prandtl number. You will notice that some of the properties will of course be temperature dependent, and in general when you're evaluating the Reynolds number, Prandtl number and Nusselt number, if you know how those properties vary with temperature, you would evaluate them at a temperature that's the mean of the wall temperature and the far field temperature. This is known as the film temperature. If you have flow of a flat plate but there's uniform flux from the plate, then slightly different equations apply. You'll see that actually the form looks relatively similar, but for example now in the laminar flow condition, the Nusselt number equals 0.453 times the Prandtl number to a third times the local Reynolds number to a power of a half, and that's a change from 0.332. And when we move to the turbulent condition, it turns out the local Nusselt number is equal to 1.04 times the Nusselt number that we'd have calculated previously, so we end up with a slightly different result at the end, that the local Nusselt number equals 0.0308 times the local Reynolds number to the power 0.8 times the Prandtl number to a power of a third. So what I would like you to do for next time is to take the information given here and calculate what the average heat transfer coefficient is if the plate is 0.1 meters long, 0.2 meters long, or 1 meter long. And you can use the equations on the previous slides, and you'll note that the plate is at a fixed temperature. So what I've done overall in this session is introduce some ideas around viscosity, and then moved on to look at boundary layers, the fact that temperature changes and velocity changes in convection conditions basically occur near the surface of the object that we're dealing with, and that the thermal boundary layer and the viscosity boundary layer are unfortunately usually different thicknesses. I've then looked at dimensionless numbers, specifically the Reynolds number, Prandtl number, Nusselt number and the Grashof number, and pointed out that for forced convection the Nusselt number can be related to the Reynolds number and Prandtl number. You get different relationships for different geometries. And similarly for free convection, the Nusselt number can be related to the Grashof number and the Prandtl number. And I showed some examples for flow of a flat plate under forced convection conditions. And the point about these relationships is the fact that you can start with some fluid properties which will allow you to calculate the Reynolds number and the Prandtl number. Having selected the appropriate relationship, you can calculate the Nusselt number, and from that you will then be able to calculate H for the particular circumstance that you're dealing with, i.e. this gives us a way of obtaining values of the convective heat transfer coefficient for different fluids and different geometries. Thank you.